Now this illustration deals with calculating the fault current. NEC 110.9 basically says that we shouldn't be blowing terminals loose, damaging conductor insulation, termination lugs, and so forth due to the available short circuit current. We must be able to interrupt it. 110.10 says we can use anything that would throw up a resistance to the flow of the available short circuit current, which would be the effective fault current path. Now, we know we can use Table 8, Table 9 and get a good round figure to go by. Now, let's review the equipment ground with the boxed in information to the left. And notice branch circuit, equipment grounding conductor, finding known values, the 100 foot, going to the table, 8 or 9 and pick it up. 9 would be more accurate, you know, if you were using metal conduit and knew what it was metal or non-metallic, whatever you were using. But 100 foot, number 12 was 1.93 was our resistance. And when we did the math to get the total resistance of that 100 foot run, you divide the 100 foot by 1,000 foot times 1.3 ohms, and we come up with 0.193. Now the feeder, 100 foot, number 8, and the table listed 0.778 is our resistance, or resistivity, if you want to call it. And 100 foot of it divided by 1,000 foot times 0.778 would give us 0.0778 is our resistance for that total run. Now, the total resistance added together, the branch circuit, we had 0.193. The feeder, you had 0.0308 for the phases. But for the equipment grounds, that's what we're wanting to flow back. Go to the right of the step 1, and it's 0.193 plus 0.0778, giving you a total, when you added them together, of 0.4946. Now, that's the branch circuit and the feeder added together. Now, notice that's coming, bringing the ungrounded circuit conductors to the point where the fault developed, and the return. That's why in step 2, you get 0.386 for the branch circuit. It's ungrounded going and equipment ground coming back. Same way with the feeder. That's why we got 0.1086 is our total resistivity or resistance. Adding them together, 0.4946. The current then would be 120 volts divided by 0.50, because it's 120 volts to ground system, and we'd have 240 amps that we would have at the point of that fault in the illustration from at the branch circuit feeding the equipment. And that's all you'd have. And you know yourself, in times past, we used to carry a number 12 wire, strip it on the end, solid, and we just kind of beat the copper into a little blade, and we just stick it in a plug, say a receptacle, and you just hear like that. But as we worked that wire out and got closer back to the panel, the effective fault current got higher. And we knew from our experience, you didn't go up to the panel board and short anything out. We'd get all that wire ahead of us with all that resistance in that wire ahead of us, and through bus and everything else and panel boards and all that added together, we'd get a very low available short circuit current. And more than likely, it would be lower than what you see in the calculation. But that's a good method to go by. But because you can use your code book and do this, and just use your your iPhone with this calculator to do that. And if you got one of those iPhones that had where you could build in your formulas, I know you can get a little handheld calculator from TI to do that. And then all you have to do when you put the formula in that you see up there, just put your values in, it'll tell you right quick. Or you just say, no, this panel board is 10 kA, and all my breakers in there and equipment is 10 kA or less, then you know you're going to interrupt it. If it's an old existing panel board based upon a good while back, take 80%. And if you had, say, 10,000 amps hitting the panel board, it'd be 80% of that. So we just take 10,000 IC rated equipment. Say you had 10,000 amps, 10 kA, take 80% of that and figure 8,000 amps, say, at the panel board. And we usually do that. But now we got a better deal going for us because 110.24 says you got to put it on the panel board if you don't have qualified people at a facility doing the servicing and qualified engineering, and you go under the exception to 110.24. And, you know, we kind of call that out. So what we're doing here in the 0.4946, we round up to 50. You always round it up. And divide that in the voltage to ground, and you get a very, very close calculation of what would be there. So just in your mind, think, if I took that branch circuit out and got a fault at the feeder location, it's going to be higher. Take the feeder out, get back at the service, and it's going to be much higher. So many times at a service, especially in a big commercial facility or an industrial plant, you're working on a stick of dynamite at that service if you do not have some kind of energy reduction devices, fuses or circuit breakers, which we looked at in Chapter 9 and talked about and gave you references to 70B and 70E, where you could just pick up all the information you needed to know about these devices. But you must be qualified to set them and put them in their settings so that they are accurate and they sense instantaneous. And then when you set them in a certain setting, the instantaneous is gone. They clear quick and lower the energy because it regulates the amount of time the current can feed the arc in the location where you're working. So you read all that in our, Chapter 9 of Volume 1 of Stallcup's Electrical Design book, or any other book that you choose that would give you this information. So this figure 16-25.3 is a summary of your figure 25.1 and .2. That information now has been collected and the calculation performed here.